Right. So I hope that you can see this slide. Okay. So for today, actually, mode of teaching is in a two ways. All right. So actually, I already uploaded the videos again inside the future. So if you look out into the lesson plans, right? So should we should cover okay from the week 1 to 3. Okay, we should week 2, 3, 4 we should cover on the type of molecular diffusion. We're going to start with the gases, molecular diffusion in liquids, and molecular diffusion in solids. But my plan is that since this week 1, 2, 3 is in online version, so perhaps that I would like to cover all the syllabus of this topic to within these three weeks. All right. So when we meet later during the week 4, and then we're going to have the tutorial class. Okay. So untuk for today's lesson, all right. For today's lesson, we're going to cover the molecular diffusion in gases. And should you know that under the molecular diffusion in gases, there is 5 subtopics. Okay, so the first one, it should start with the equimolar counter diffusion. And then the second one, we are talking about diffusion. So you can see here that if we are talking about diffusion, the notation is GA. We are talking about the diffusion plus convection. The notation is the NA. And then we're going to talk about several examples of the diffusion plus convection. So in our case, we have 2 cases, okay? So the subtopic number 3 is the solid A, okay? Not a diffusing, but a solid A diffusing through a stagnant non-diffusing B. And the fourth one, we're going to talk about the diffusion through a varying cross-sectional area. Okay, and the last one is the determination of the diffusion coefficient for gases. Okay, so that's the syllabus that cover under the topic of diffusion in gases. All right. So basically, if you find it difficult, okay, to have a live lecture, okay, to have this live lecture, all this syllabus already has been covered inside the future when I uploaded about 4 videos relating to this molecular diffusion in gases. So perhaps that so for today's class, there is some part that maybe I'm just skip so that you're gonna learn it, especially in terms of the derivation of the equation. Okay, perhaps I just skip that part and then you're gonna look into that parts inside the video. Okay, all right. So usually for the question that might comes in the assignment, midterm assessment and the final assessment, all right, if I look into the trend, usually for the MTA and final examination, because it is a closed book examination, so usually there is no question asking about the derivation of the equation, okay, derivation of the equation. Okay, so by right, all the final equation, okay, we have a lot of equation that we're going to need to apply for different cases of diffusion and convection. They're going to put it inside the appendix, and you need to have the ability to select the correct one. However, this kind of question asking about the derivation, everything might be asked during the assignment. Okay. So you know that the assignment, the concept is assignment is that it's an open book test. All right. Even though that's, for example, that the assignment one is the individual, but still you can have some kind of like a discussion between your friends. You can refer to the book. You can accept that you cannot ask me how to solve the question. Okay. That's the thing about the assignment. Okay. Now we go to the molecular diffusion in gases. We talk about the first cases is the equimolar counter diffusion. So equimolar counter diffusion is very easy case where we assume, okay, that if you imagine that you have a 2 large chamber connected by a tube, right, and inside that you have 2 different type of gas that we're going to label as a gas A and the gas B. All right. So in the concept of the equimolar counter diffusion, all right, the GA is equal to negative GB. And then we need to prove that the DAB is equal to DBA. So usually for the question that might come under the subtopic equimolar counter diffusion, The first one is that you need to prove that the DAB is equal to DBA. Okay, so the question have come before, I think, kat mana keluar, I'm not sure lah, tapi in assignment perhaps, okay, I already forget. Okay, they ask you to prove how the DAB is equal to DBA. All right, that's the first thing lah. And then the second one is that you need to calculate the flux of the GA, and usually the question for the equimolar counter diffusion, you need to prove that the GA is equal to negative JB. So if the question of the equimolar counter diffusion relating to the calculation, it's a bit easy because you just need to use the equation and put the value inside the equation for you to get to solve the problem. Okay, so for the derivation part on the how to prove that the DAB over DBA, you need to remember certain things. Okay, you need to remember certain things. For instance, that okay, it start with the JA is equal to negative JB. All right, and then you must remember that okay, the first question is that the JA is equal to negative DAB, the change of concentration dCA over delta Z. Okay, you need to remember this one. And then for the JB, it's negative DBA, this dCB over dZ. So right now we would like to prove that the DAB is equal to DBA. So please recall that why the notation of negative here, because this CA2 minus CA1 or the CB2 minus CA1 will give you a negative sign. Okay, because the concentration and point 1 is always bigger at the concentration for compared to the concentration in point 2. So that's why we put a negative here so that you're going to have the positive value of GA. Okay, so what you're going to do is that here that JA, okay, is equal to negative DAB dCA over dZ, and it is equal to negative JB. All right, so which is kenapa ya tertutup? Just wait for a while. Okay. Perhaps I should use a different platform. Okay. Okay, can you see again the screen? Okay, 6 times. Sekejap, tak keluar pula ni. Where are we? Okay, so the negative JB here, okay, is that is equal to negative, all right, and then negative dBA dCB over dZ. Okay, so that's the negative sign and negative sign is cancelled out here. So JA is equal to negative DAB dCA over dZ is equal to dBA dCB over dZ. Right. So okay, this is just a rearrangement from the equation 1 and 2. Okay, so you know that inside the closed chamber, okay, for the case of the equimolar counter diffusion, for a closed chamber, inside the closed chamber, that the total pressure is actually the summation of a partial pressure of A and plus partial pressure of B. Okay, so that's for the pressure, and it's actually the same thing for the concentration. Mean that if you have a closed chamber and you have a mixture of A and B inside that, however the A goes to the left or right or B goes to the left or right, the total concentration inside that is still the same, right? So sama juga, the C here is referred to the total concentration, right? Total concentration, and is equal to the Ca plus Cb. The concentration attributed by the component A plus the Cb. Okay, so if you differentiate the both side, okay, dCA plus dCb is equal to dC, and you know that it is equal to 0. Means that there is no change of the total concentration inside the closed chamber, and dC is equal to 0. That means that the dCA is equal to negative dCb. Okay, so to solve this problem, to show the DAB is equal to DBA, this is the part that perhaps the student might forget, and you cannot solve this other things, right? So this is how you're going to prove that the DCA is equal to negative DCB. So here, if you put negative DAB, so DCA is actually equal to negative DCB over DZ, right? And equal to dBA dCB over dZ. So negative sign and negative sign here. So you can see here, we can prove that the DAB is equal to dBA. Right? Okay, so that's about the derivative, the proof of the DAB is equal to dBA. Now we go to the solving the question related to the equimolar counter diffusion. So usually the question is quite straightforward. Okay, for this case, because you're just gonna apply the equation of flux. So by now you should familiar with this equation of GA. So GA, we are talking about apa? GA is equal to negative DAB dCA over dZ, right? So it's also equal to what? Negative DAB CA2 minus CA1 over Z2 minus Z1. Okay, so if you would like to change it into the CA1 minus CA2, then this negative sign will be eliminated. DAB is equal to CA1 minus CA2, Z2 minus Z1. So this is the equation that when you are dealing with the liquid, right? So when you are dealing with the pressure, as I mentioned to you before this, okay, then you change into the PA1 minus PA2, but this RT will emerge inside the equation coming from the correlation of PV is equal to nRT. Okay, so look out into the question here. Boleh baca dulu, boleh tengok solution tu. Ammonia. So that the Z is 0.01 meter. Given to you the pressure, temperature. The value of PA1 is given. PA2 is given. And then the DAB is given. Okay. So the good practice is that for this one, to ensure that we will have a correct answer and an answer, a final answer here, please make sure that you insert the unit inside this equation, right? So that we're gonna ensuring that. Okay. So it's simple, right? So just let me explain. For this subject, or I think that the whole engineering subject, it's very important for you to put the unit of the value here. So usually that the mark is given. So let's say that the final marks is 2 marks. Okay, one is contributed by this value and one contributed by this unit. Alright, so you please remember that whenever the value of you put it inside your answer script, it must come with the unit, right unit. You will get the marks for that. And also another one is coming from the solution. You need to show how you get this final answer. So let's say that if you have just putting the value of JA sama dengan DAB, PA1 minus PA2 over RT delta Z, and suddenly you get the answer of 4.7 to the power of negative 7 means that you doesn't have a marks for the solution. Okay, you need to look to show it how you get the value. Okay, so for this example, it's not very good because it doesn't put the notation of the unit here. So perhaps we can just simply do it. JA is equal to 0.23 to the power of negative 4, and the unit is in a meter square per second. Okay, and then you multiply with this one, and the unit is apa sekarang ni? Pascal. Okay, the unit is in Pascal. So you put the value. I just put the unit. Just want to ensure that the right unit, right? So 8314. Okay. So this value is given inside the table. We have a lot of a value for the R constant. It a bit different according to the what types of unit. So how to select the R constant is by looking at our unit for the system lah. Since let's say that now our pressure is in Pascal, right? So that's why in this case they are using the 8314 for the unit of meter cube, Pascal, kilogram mole dot K, and then you multiply with 298 Kelvin, and then we have the delta Z here, right? Sorry, delta Z patutnya kat bawah. Okay, ada delta Z kat sini in unit meter. So if you cancel out, okay, Pascal kat atas, Kelvin kat atas bawah. Alright, so we have a meter cubic here, a meter square here, you cancel out, and then you can see that the unit is in a kilogram mole meter square dot second. Right. Okay. So so you should get the correct answer. So in this case, it's quite straightforward because the unit of the pressure, for example, is similar, and then the unit of the length is given in meter. Okay, so sometimes students just make a mistake by confusing between the unit of the cm and meter. Of course, when the unit of the cm, you need to multiply with it to the power of negative 2. Okay, so when you do this, solving this problem, okay, you need to prove that the JB, okay, you must prove that the JB, the value and the unit must be similar with the one with the JA, only that the different is the negative sign here. Okay, if this kind of question coming out during your MTA means it's a bonus question for you, all right, for you to solve it because it's just quite a simple question. Okay, so right now we know that you just made a statement here that we know that the BA is equal to DAB coming from the above solution, right? So we can use the same value of the DAB. But right now, RT and delta Z is similar with the previous one, only that now we change the PA1 into the PB1 and PA2 into the PB2. So here is the relationship. Okay, you know that the inside the chamber, okay, the total pressure is the PA1 plus PB1. Okay, A at 0.1 and partial pressure of B at 0.1. Okay, so I hope that you can understand about this one. Okay, so now we go to the second part. Okay, the second part is actually on the explanation about the diffusion of gases A and B plus convection. So before that we go to this part of the revision, okay, sebenarnya saya tak nak go detail sebab ni kamu boleh tengok dekat dalam video. Alright, bahagi molecular diffusion in gases part 2. It's only about 5 to 7 minutes video. Alright, so first you need to know what is the difference between the diffusion and convection. Okay, usually kan saya kata hari tu memang ada soalan akan ditanya lah, give the similarity and the difference between the diffusion and convection. So antara yang paling jelas ialah diffusion ni adalah proses yang lambat and convection ni adalah proses yang cepat. And usually diffusion ni dia melibatkan molecule level, convection ni dia melibatkan bulk flow. Alright, so some cases, okay, some cases dia melibatkan kedua-duanya. Okay, diffusion plus convection. So how actually we would like to calculate for the flux. Okay, kita tak boleh nak ignore the part of the convection dan just focus pada diffusions, but the convection does exist. So how we would like to integrate the convection inside the equation. Okay, so I think that this part, okay, I just wanted to skip here. Okay, you can watch out it inside the video, but I just would like to emphasize that if you are talking about the flux contributed by the diffusion, the notation is J. But right now we have a new notation we're gonna write down as a NA. However, the NA having a similar unit with the GA as well. Okay, so kalau GA unit dia kilogram mole per meter square dot second, centimes goes to the NA. NA pun sama juga. Okay, kena hafal lah sebab dalam kita punya syllabus ni kita gunakan apa? SI standard unit SI, so it must be in a kilogram mole over meter square dot second. So automatically you know when the notation is changing to the NA. So in the case of NA, maksudnya proses ni dia melibatkan diffusion plus convection. Okay, so it's just the same thing. Okay, I mean not the same thing, it's different, but it's still talking about the flux, the movement of the mass. Alright. So for our syllabus, under the molecular diffusion in gases, we're going to talk about two cases that using this NA. Okay, the first one, okay, now we go to the, saya pergi laju sikit sebab memang maybe about our later balance satu jam lagi tu kamu boleh tengok video. Okay, alright, so kalau tengok dekat apa orang kata subtopik yang 3 under the molecular diffusion in gases, we are talking about the solid A. This is not a diffusing, but it's a solid A. Okay, diffusing through a stagnant non-diffusing B. Okay, if you read here, okay, now in this slide, we have the most two common example talking about the solid A diffusing through a stagnant non-diffusing B. Okay, in this case, one boundary at the end of the diffusion path is impermeable to component B, so it cannot passes through. Okay, so there are dua contoh dekat sini untuk kamu faham. The first one is when we have a narrow test tube, okay, inside the laboratory, okay, we can find this thing, okay, a narrow test tube, and we have the liquid of benzene inside there. Okay, so the evaporation of the pure liquid benzene at the bottom of the tube, where the non-diffusing air B is passed over the top. So in this case, that the benzene is a component A. All right. So the pressure at a point 1 is going to label as a PA1 is actually on the surface of the liquid benzene. Okay, so the evaporation will go to the open air, right? So we're going to put the location of point 2 just after it goes to the open air. Okay, and that we're going to put as a PA2 here. So in this case, only the benzene can actually diffuse or penetrate into the air, but the air cannot diffuse back into the benzene. Okay, so that's the first case. That's the first examples to show the diffusing through a non-diffusing B. Okay, so dalam case ni, we're going to label the point 1 here, okay, as point 1 is on the surface, so it'll become the PA1. So the point 2 is just after the benzene are exposed to the open air, so that the distance between the 1 and 2 we're going to measure label as a delta Z. Right. Okay, so in this case, usually that the PA2 is negligible or equal to 0. Inside the question, when you are inside the question, if you meet some kind of a sentence saying that the benzene is diffused into the large amount of air, okay, or that's the the concentration of benzene at the point 2 is too dilute. So means that that's a hint to show that we can assume that the PA2 is equal to 0. Dan terlalu rendah, maksudnya tekanan yang disebabkan oleh benzene tu, okay, dekat jumlah udara yang besar terlalu rendah, so that is must more or less it can be equal to 0. Okay. Okay, the second case here, again, contohnya sini dekat dalam rawatan wastewater treatment inside the plant. So you have a mixture of gases in air, okay. Usually we have a methane bercampur dengan air, or sometimes we have the ammonia gas bercampur dengan air, right? So if this kind of gas is exposed into the liquid water, all right, liquid water, please note that only ammonia, the component A, can diffuse into the water. B dia tak boleh. So dalam ni nampak kita kena tahu which one we would like to label as a A. So sekarang ni the ammonia ni, they diffuse through a stagnant non-diffusing B, which is air, and penetrate into the liquid water. Okay, kita tahu kan air ni oxygen and nitrogen, and oxygen and nitrogen is very difficult to dissolve inside the water, but not ammonia. The ammonia can dissolve easily. So this is the second case of the diffusing through a stagnant non-diffusing B. So whenever you receive a question, right, the first thing is that you need to understand the phenomena, and since that the question use the label of NA, DAB, JB, negative DAB. So you need to know how to label which component as A and which component as B. And I think that's also a skill. So that kita tak adalah terbalik, tertukar buat kiraan ke dan sebagainya. Okay. So dalam case macam ni, okay, the equation yang kita akan guna, okay, I just skip this the derivation part. Kita akan guna equation yang kat dalam kotak merah ni lah. Okay, so you can spot that it is a bit complicated compared to the GA tadi kan. Kalau GA tadi dia just apa? Negative DAB CA1 minus CA2 over Z2 minus Z1. Okay, and then kalau partial pressure kita tukarlah, ada RT semua. So dalam case ni a bit complicated because we have a convection factor. So this is the equation, okay, that coming from this one, right? Okay, so since the the component B is non-diffusing or stagnant, then NB is equal to 0. So you make some kind of like arrangement, all right, arrangement, and it become like this. Okay, so you bring all this Na to the left hand side, right? You bring all the Na to the left hand side, it factorize the 1 minus P over P. All right, and then what we're gonna do, okay, you bring this notation because we would like to integrate it towards dP. Okay, you try to solve it. Okay, you try to solve it again by boleh cuba sendiri, buat sendiri. Okay, and then finally you will have this equation. So apa yang berbeza dekat sini ialah kita still ada lagi DAB. Okay, cumanya bahagian calculation of the pressure gradient tu dia akan berbeza. Okay, so after you have this equation, we would like to eliminate the term ln here inside the equation so that you will have to calculate the value of ppm. Okay, so these tiga equation ni sebenarnya sangat berkaitan lah. Okay, sometimes usually the question that we're gonna use to solve this problem is this one. Okay, because it's quite simple and you just need to calculate the value of the ppm. So ppm tu apa? Okay, inilah definition of the ppm. Alright. Okay, any questions so far? Boleh faham? Okay, boleh, kalau boleh, boleh faham, and then cuba buat example 622 ni. Cuba example yang dua-dua ni. Ni yang saya betulkan tiba-tiba je 8314 tu betul tapi unit dia tu. Okay. 8314 J over kilogram mol dot K is also equivalent to 8314 meter cubic Pascal over kilogram mol dot K. Okay, so you read the question first. So all this question is actually extracted from the textbook. Okay. So you read the question first and extract the information. Okay, so we have here the water in the bottom of a narrow metal tube is held at a constant temperature and pressure. So given to you here is the temperature given and pressure is given. Okay, and the water is and diffused through the air, and the distance is the delta Z is given, which is 0.1524 meter. Okay, calculate the rate of evaporation. So kalau soalan kata rate of evaporation, okay, the calculate the flux, okay, maksudnya kita nak kira apa? The rate of diffusion and plus convection tu, right? And the diffusivity of water vapor at the specific temperature and pressure is given to you as 0.25 darab 10 / negatif 4 meter square per second. Okay. Alright, so dalam case ni, okay, first we just need to, okay, now dalam case ni kamu kena detect dulu, okay, this case talking about which cases? Is it talking about the equimolar counter diffusion through stagnant and diffusing air or varying cross-sectional area? Only that we can select what types of equation that we're going to use, okay? So dalam case ni kita nak guna equation yang ni, alright, this one. So dalam case ni you can see here that the DAB is given, P and T is known, R is a constant, Z2 minus Z1 is given, And PBM, you need to calculate it from the value of PA1 minus PA2 first. Okay. All right. So here you know that the PA1, okay, at point 1, refer to the partial pressure on the surface of the water. And then the PA2 is when the water is exposed to the open air. So as I mentioned before, when this small amount of water, okay, is exposed into the large amount of air, we can assume that the value of PA2 is approximately equal to 0. However, what about the PA1? Because it seems that the value of PA1 is not given inside the question. Okay. However, we know, right, as an engineer, you know about the concept of the vapor pressure. Okay. Okay, vapor pressure is not similar with the partial pressure. The partial pressure is something that is exerted or contribute by the specific molecule. Okay, contohnya kalau sebab tu dia punya formula dia apa? YA P sama dengan PA. Okay, ni adalah partial pressure. Tapi vapor pressure, okay, you know about the vapor pressure if you have some kind of like bekas yang ada air. Okay, so at the equilibrium, the rate of the condensation and the rate of evaporation is similar. Okay, so kita tak nampak lah sebab it happens in a molecular level, right? But actually when we see when we have one container, we fill it in the water, actually there is a molecule of water escape, become vaporized, and actually there is a gas molecule of water is actually condensed back into the liquid. So if the rate of the condensation is similar with the rate of evaporation at equilibrium, okay, we call it as at equilibrium, and if you measure the pressure just on the surface of the water, that is referring as a vapor pressure. Okay, as a vapor pressure. So this vapor pressure is very important later on when we are talking about designing the distillation column. So here, because our component is water, okay, so you know that we have so many data relating to water, right, as a vapor pressure. So you can actually refer to the table of the vapor pressure of water. All right, you can refer to the vapor pressure of water here. Okay, so how to say? Okay, if you look out into the kalau ada lah, kamu ada buku textbook. Okay, find a vapor pressure of water. Because I'm using the old one, okay, if the new one, perhaps the level of the table might be a bit different. Okay, biasanya vapor pressure of water or any vapor pressure is actually influenced by the temperature. So it means that the higher the temperature, the higher the water vapor pressure. Okay, so dalam kes ni, vapor pressure dia bergantung kepada kamu punya temperature. So dalam kes ni, kalau temperature 293, maksudnya kena tengoklah dekat 293 ni, dekat 20 degree Celsius ni, berapa dia punya vapor pressure. Okay, so even though this one is not given inside the question, but still we can find the information. Like say that this water is replaced by the benzene, kan? Contoh tadi itu benzene, then you can find the vapor pressure of benzene and look out at the specific temperature, what is the value of the vapor pressure, and that corresponding for the value of the PA1. Okay. Alright, so PA1 here, if you look out into the table, the answer is bagi dalam bentuk unit mmHg, 17.54 mmHg here. Okay, so dalam kes ni kita tak naklah guna equation ni dalam unit mmHg kan, kita nak guna at least dalam Pascal or ATM, the one that we are most familiar with. So in this case, you just change this mmHg into the kilopascal. Right. So PA1 just tahu kan, maksudnya 1 ATM sama dengan 760 mmHg. This one you are learning, you learn this one inside the CPP1, okay, last semester. And then it's also equivalent to 101.101 okay lah, kilopascal, right? Okay, so we have the value of PA1 right now and we have the value of PA2 kosong. So you know the correlation of P is equal to PA1 plus PB1. So maksudnya kat sini PB1 tu sama tolak je lah, P minus PA1 here. You will get the answer. Okay, PB2 pun sama juga. total pressure dapat kat mana? Kat sini kan. Ni total pressure. Okey, tolak kosong dapat ni. Dapat nilai PB1, PB2. You can calculate for the PBM. So dekat sini lebih kepada kamu kena hati-hati dalam pengiraan tu. Alright. Because it's quite direct question. Okay, it just dia tak adalah melibatkan numerical analysis ataupun difficult integral or whatever. Okay, dia hanya melibatkan a direct equation that you just need to put the value. So what you're gonna the tricky part is only about the unit. Okay, and then yelah nak kira kan, nak kira long semua. Sekarang saya pun salah juga. Okay, it's common. So this is the good practice, right? You can see here that it puts the dia letakkan. Okay, so I would like you to have this kind of things lah inside your assignment. Okay, nanti dalam midterm assessment letak unit dia, meter square per second, and then darab dengan total pressure. 10/5 Pascal. Lepas tu darab dengan apa? Darab dengan total pressure. Okay, and then unit di Pascal juga. Sorry, bukan total pressure. Pressure difference. Alright, and then kita ada apa? Darab dengan 1/8314 meter kubik Pascal kilogram mol dot K, and then darab dengan 293 K, darab dengan 0.15, darab dengan PBM. Okay, PBM. So nampak kan kalau kamu selesaikan tu, dia boleh all the units cancel out and eventually you will get the value of the answer, the unit of a kilogram mole over S dot M square. So regardless what the difference value of R, okay, some student they prefer you guna pressure in ATM instead of Pascal. Okay, it doesn't matter lah, maksudnya mungkin nilai R kamu nanti, nilai R kamu akan berbeza. Okay, jadinya itulah maksudnya apa? Maksudnya kalau kamu gunakan nilai R berbeza, unit berbeza, tapi kalau betul it boleh cancel out. Okay, semua akan dapat jawapan akhir yang sama, unit yang sama, which is kilogram mole per S dot M square. And please take note K mole sama dengan kilogram mole. Okay, kilogram mole adalah mole dan bukan kilogram. Okay, so I guess that's we settled the first part. Then we go to the next one, which is the kita pergi yang kedua, yang keempat, subtopik keempat under molecular diffusion in gas, which is on diffusion through a varying cross-sectional area. So ada soalan ke sebelum tu? Faham ke yang kita buat solve tadi tu?
Faham.
Tak faham? Faham senang je kan? Alright, so right now we are dealing with the second case of NA. So dalam syllabus kita, kalau kita nak guna NA tu, kalau equimolar counter diffusion, the notation is JA. Okay, kalau NA, dia either stagnant or diffusing B, or diffusion of component A through a varying cross-sectional area here. Okay, so you can take a look, baca dulu ke slide ni sekejap. Okay, so as I mentioned to you, okay, the derivation of this equation, okay, saya jump terus lah. Alright, untuk case diffusion through a varying cross-sectional area, the final equation that we're going to use is in this one, in this blue box here. Okay, so perhaps you can spot the difference right now. That the delta z is replaced by the r, which is the radius. Okay. So dalam case diffusion through a very cross-sectional area, the most famous example we're going to use is the naphthalene ball. Ataupun naphthalene ball ni kita panggil dalam bahasa kampung ni ubat gegat lah. The one that we beli kat kedai DIY tu, and then kita letak dekat dalam almari kan untuk apa, untuk menghalau lipas semua tu. Okay, so if you notice that by time the size of this naphthalene ball will reduce. Okay, so that this naphthalene is actually slowly diffused into the open air. Alright, so that the diffusion is actually berbeza sebab makin lama the surface area become smaller. Okay, that's the first case. And the second one is when we talk about the diffusion through a circular conduit here. Okay, we have some kind of conduit that have a different surface area at the beginning and at the end. Okay, all right. So for the first case, this is the derivation of the equation for the case of diffusion through a varying cross-sectional area referring to the naphthalene ball. Okay, for this part, the second one, the diffusion through a conduit of non-uniform cross-sectional area. Okay, this is the final equation. However, not inside the green part here, inside here, however, the solution for this second one is usually will be accurate if you are using a numerical approach. Maksudnya kena guna Microsoft Excel macam tu. Okay, so in that case, that's why for the subject, usually when we talk about the diffusion through a very cross-sectional area ni, kita hanya fokus pada case yang pertama sahaja, iaitu diffusion from a sphere. Okay, so diffusion from a sphere ni dia tak semestinya naphthalene ball. Okay, dia boleh juga ada evaporation of a drop of liquid, ataupun naphthalene ball, ataupun the diffusion of nutrient to a sphere like microorganism in a liquid. Okay, so whenever you read the question, alright, first please detect what type of what we call it, apa fenomena yang involved kat dalam case kita ni. Okay, only then you can pick up the right equation. Okay, so kalau kamu detect contohnya sekarang ni melibatkan diffusion of nutrient to a sphere like microorganism, and then you know that this is the equation that we're going to use. Alright, so in other words, lagi senang ialah biasanya kalau soalan tu kan kita baca and dibagi radius, right? The radius is 2mm. Usually, biasanya kalau ada radius dibagi, kita tahu ini mesti nak kena guna equation yang ada radius ni, which is this, the one is inside the blue box. Okay, kalau tak, dia tak akan bagi radius, dia akan bagi jarak kan, jarak, the length of the tube. Okay, alright, so that's the thing lah. So as I mentioned to you that this class for today is a hybrid mode. Part of the lecture, okay, especially in terms of the derivation, you can see it, okay, watch it inside the future. Okay, now I would like to focus on how to solve this problem. Okay, this example 6.2.4. Can you first read the question? Baca dulu soalan. And then cuba buat tanpa melihat kepada solution kat bawah slide ni dulu. Okay, so macam mana? A sphere of naphthalene having a radius of 2 mm, 2 millimeter is suspended in a large volume of still air. Okay, given to you the radius. Okay, kita kena extract maklumat dulu. Radius is given. The temperature is given and the pressure is given. The temperature berapa? 318 K. The surface temperature of the naphthalene can be assumed to be at 3 apa ni? The surface temperature of the naphthalene can be assumed at 318 K, as vapor pressure at 31 K is 0.55 mmHg. So from this sentence you should understand, okay, apakah maksud 0.55 ni, kan? So you know that if you have this cache here, the point 1 is referred to the surface of the naphthalene. So we're going to label here as a PA1. Now it diffused to the open air PA2. Right, this PA2 is the air. Okay, bukannya air, maksud saya diffuse into the air. So we can imagine that the PA at the point 2 is very low, that we can assume that this PA2 is approximately equal to 0. Okay, so okay, so the surface temperature of naphthalene and the vapor pressure. So tadi saya baru cakap kan, what is the vapor pressure? The vapor pressure is the pressure that we measure just above the surface of the upper solid or the liquid, right? Okay, so right now we know that this 0.555 mmHg is actually referred to the PA1. Okay, boleh So sekarang ni kita tahulah Kp sama dengan 1 atm, PA1 sama dengan 0.555 mmHg, and the value of DAB is given in the unit of the meter square per second. Alright, so tak apa, teruskan. Tak payah tunggu saya. Okay, so right now you have the notes with you, right? You have the notes with you. Alright. So the equation that we're going to use is that the NA1, okay, inside the blue box. NA1 is the DABP PA1 minus PA2 over RT R1 PBM. So nilai RT R1 dah tahu, DABP PA1 PA2 dah tahu. The only things that we doesn't know is the PBM. So if you look out into this question in here, kan, ada benda yang kena hati-hati in term of the unit. Kalau kamu ambil je semua value tu masuk dekat dalam equation, and it will be totally wrong, kan? Sebab apa? Sebab nilai PA1 tu kena tukar dulu daripada mmHg, kena tukarlah kepada Pascal, kan? Lepas tu R1 ni pula dalam unit mm, kan? So kena tukar kepada unit meter. Okay, this is the small things that I sometimes do not emphasize to the student. Okay, but this is the things that you make a mistake during the MTA nanti. Okay, alright. So, okay, and then they are using the same R as before, 8314 meter cubic Pascal kilogram mole dot K. Okay, kau tengok dekat equation kat bawah ni. Tengok dekat equation kat bawah ni. Apa dia? Okay. Instead of they are calculating the value of PBM by using the equation, you know, the Aldous Loan, dia hanya guna average value sahaja. PBM sama dengan PB1 plus PB2 over 2. However, this case is only acceptable if the value of PB1 and PB2 are close to each other. Barulah kita hanya ambil average ni sahaja. Okay, so you can try to solve it. Kena buat, kena biasakan buat. Okay class, you try to solve it and then kita take 5 Okay, kita sambung pada pukul 11.05 nanti. Okay, so far ada masalah ke untuk faham example 624 ni? Okey tak setakat ni? Untuk 624, okey tak?
Okay, doktor.
Alright, so sikit lagi, okay. Just I nak go through this one and then kita boleh, and kita akan jumpa lah next week hari, apa kita cuba hari Rabu kan? Right, hari Rabu minggu depan. Okay, so sikit lagi. The last topic for the diffusion coefficient for gases is on the how to determine, how to calculate by using the equation. So you all know, right, that when we would like to calculate for the value of Na and Ga, nak tak nak dalam both equation ada nilai DAB. This DAB is referred to the diffusion coefficient. And this diffusion coefficient is something, is the things that difference between the species inside the different medium. For example, that if you have a nitrogen ammonia gas, if it dissolves inside the air, and then the DAB will be different. If you have the ammonia diffuse inside the nitrogen, and the value will be different. Okay? And these things need to be determined by using the experiment. Okay, it's not the thing that we can calculate macam kita nak kira flux semua ni. Okay, kita kena by accurate, dari segi accuracy-nya kita memang kena buat eksperimen to get the value of this DAB. Alright. However, for the common system, okay, maksudnya untuk sistem yang dah biasa, nilai DAB ni orang dah buat establish, maksudnya orang dah buat eksperimen and then kita dah dapatkan nilai DAB. So this experimental diffusivity data, okay, inside the old textbook is referred to the table 621. So table ni ada dekat bawah ni, table 621 ni, nampak tak? Okay, you can kita tengoklah ya dekat kamu punya textbook tu, cari table ni. It might have a different different table lah, mungkin table lain. So kalau kau nampak dekat sini, apa ya? Okay, this is the value of this DAB. Nampak kat sini, this is diffusivity. Sebelum tu saya nak cakap yang okay, if you can spot here, okay, this a diffusion coefficient of gas at 101.32 kilopascal pressure. Okay, so for the air of ammonia at the 273 Kelvin, so this is the value of diffusivity DAB. Okay, so you know that for the case of gas, the value of DAB here is very much influenced by the temperature and pressure. So this table hanya merujuk kepada pressure 101.32 sahaja ataupun 1 atm. So let's say that you have the air and ammonia system. It happens at 273 Kelvin. However, the pressure is at 2 atm. Ataupun 2 kali ganda dekat sini. You cannot directly take this value. Okay, you need to do the correction factor. Okay, the one that we're going to learn after this. And you also note that here we have the air and H2O system, and it's given to you at a different temperature here, right? 0, 25, 42. Okay, it's also, okay. So you can see here that is also influenced by the temperature. All right, so the correlation is that the DAB is correlate with the T to the power of 1.75 over pressure. Okay, then this is one is only valid for the DAB for a molecular for of molecular diffusion in gases. Alright, so kita boleh tengoklah contoh-contoh common here. So biasanya hanya beberapa sahaja yang dibagi pada temperature yang berbeza kan. Macam dekat air dengan water ni 0.25-42. Kalau air carbon dioxide dekat suhu 3 dengan 44. Kalau okay dan seterusnya. Okay. Alright, so if you are dealing with the system, with the common system, then okay, you can refer to this table. However, sometimes, especially during your design project, kan, kita akan jumpalah sistem yang pelik-pelik kan. Kita tak ada pun dekat dalam buku semua tu. So, we need to make some kind like a calculation or the estimation. Okay, kita kena guna equation untuk cari nilai DAB. Bila cari nilai DAB ni, barulah kita boleh kira nilai GA atau NA, kan? Matlamatnya bila kita nak kira, biasanya kita nak cari nilai GA dengan NA. Dan dalam equation GA dengan NA ni, dua-dua ada term DAB, kan? So DAB ni nampak tak? Dia bagi dalam soalan, dia suruh kamu tengok table ataupun kamu kena kira sendirilah. Alright, kamu kena kira sendiri, barulah kamu boleh jawab nilai, kamu boleh kira nilai flux the NA. Okay, kita ada dua equation kat sini, the Leonard Jones and the Fuller method. Alright, we have the Leonard Jones and the Fuller method here. So this is the equation. Alright, so I would like to sebelum orang tanya, saya terus beritahu yang untuk equation Leonard Jones tu perhaps because it have a not so familiar term such as the average collision diameter and collision integral based on the Leonard Jones potential. So what thing happens is that we know that the DAB, the final unit is in a meter square per second. However, in this case, when we put the value of the temperature in Kelvin, pressure in apa? Tak cakap kat sini. In ATM, right? Molecular weight in a kilogram over kilogram, you cannot. But the final unit, you cannot get the meter square per second. Alright, so perhaps that has to do with the average collision diameter and collision integral based on the Leonard Jones potential here. So if you were to use this Leonard Jones, make sure that you are putting the right value with the right unit. Okay, maksudnya sekarang ni kalau nak dapat DAB ni dalam unit meter square per second, pastikan temperature yang kamu masuk ni mesti dalam Kelvin. Pastikan yang pressure ni dalam ATM dan bukan Pascal. And pastikan yang kamu punya molecular weight ni insyaAllah tak bertukar lah. Okay, kilogram over kilogram mole. Okay, only that you only can solve this equation if you have this additional data lah. Average collision diameter and collision integral. Dan biasanya dua data ni akan dibagilah dekat dalam soalan so that barulah kita boleh kira nilai DAB and the final unit is the meter square per second. Okay, so this is the first one, refer to the Leonard Jones. The second one is the Fuller method. Okay, Fuller method is actually a simplified version of of the Leonard Jones. You can see here that the question is a bit simple compared to the previous one. Kita ada term yang familiar kan, kita ada temperature, molecular weight dengan pressure. The only things yang kita tak biasa adalah this small v here. And then so please take note that this v here is not a velocity. Biasanya kalau small v kita refer to velocity, right? In fact kat dalam topik 3 nanti pun kita ada guna nilai velocity v. Tapi dalam case ni v here refer to the sum of a structural volume increment. And how to get this value is by referring to the table 6.22 here. Okay, ni table 6.22. So again, in a new version of book, perhaps that the level of the table is different, but it's still a similar content, which is on the atomic diffusion volume for use with the Fuller equation. Okay. So macam mana kita nak kira nilai summation of the VA and VB ni? Kamu kena tahu dia punya chemical structure. Okay, contoh kalau methane apa? Methane CH4, etanol apa? Metanol apa? And sebab dia berkira tu berdasarkan jumlah atom. Alright. However, if you are talking about diffusion volume with the simple molecules, kalau macam H2 semua ni, air ni dia bagi terus lah nilai dia berapa. Dia tak payah nak kira-kira lah. Alright, so that's the thing lah about the subtopic number 5, the diffusion coefficient for gases. So right now, can we go to the last part? Okay, yang bahagian ni kita masuk minggu depan lah, tak larat cakap lah. Okay, so kita last part ialah yang ni lah, example 625. Alright, it's very straightforward. Okay. Allah Akbar. Normal butanol is diffusing through air. Okay, we have a space that filled with the air, and then you have a butanol gas diffusing through the air at 1 atmospheric pressure. Dia kata by using Fuller method, kita nak agak berapa estimate the diffusivity of DAB at the different temperature here. Okay. So the different temperature, kita ada temperature 273 Kelvin, 0 degree Celsius, right? 273 Kelvin. Okay, and then okay pada suhu 25.9 berapa Kelvin? Okay, A dengan B adalah pada 1 atm and C is at 273 Kelvin but at 2 atm. Okay. So means that the objective is that we want to use this equation. So you need to, okay, kalau untuk A maksudnya apa? Maksudnya T273, P sama dengan 1 atm. MA dengan MB ni adalah molecular weight of, so tengoklah, MA is a molecular weight of butanol, MB is a molecular weight of air. Kan? So untuk TP dengan capital M here is a well known. Okay, we are talking about molecular weight, temperature and pressure. So now you just need to focus on how to calculate this value of VA and VB here. Okay. Alright. So VA macam mana? Nak dapatkan VA. Okay, this is the VA. Sama dengan, macam mana kita nak dapatkan nilai 91.28 ni? Okay, kita tengok jap macam mana. How to get the value of VA 9128. And untuk B pula, B tu air kan, udara, terus ambil lah kan daripada sini. Okay, so kalau untuk VA ni macam mana? Okay, boleh. Agak tak dapat macam mana? 4 kenapa darat dengan 16.5. Okay, dia datang daripada atas ni kan. Datang daripada apa? Table, I mean jumlah 4, 10 dengan 1 datang daripada atas ni, betul? Nampak agak Maksudnya kalau kamu kena tahu kamu punya molecular structure tu apa, chemical structure tu apa. Contoh kalau NH3, NH3 maksudnya N mana N? Tak ada pula N. N ada sini, sorry. 5.9 darab H. Darab H pun dah. Darab 3 darab 1.98. So dia bergantung kepada kamu punya chemical structure. Berapa banyak bilangan atom carbon, berapa banyak bilangan atom hidrogen dengan oksigen. Okay. So kena darab. Okay, darab N tambah, dapatlah nilai 91.28. Lepas tu dekat air ni sebab dia common molecules. Okay, ambil je lah dekat air ni 20.1. Nampak tak ni? 20.1. Okay, dan settle bahagian extraction tu sekarang ni kena masukkan ke dalam equation. Okay, to get yourself familiar sebab ni banyak sangat kurungan, kuasa 1/3 semua kan. Kalau kamu masuk ni, dapat tak nilai 7.73 dan sebab kuasa negatif 6 ni? Cuba try. Cuba try. Dapat tak nilai 7.73 dan sebab kuasa negatif 6? Okay, mana yang dah ni cuba buat soalan B pula. B kita ubah je. Value semua sama kecuali nilai K, Kelvin. Okay, so before we end the class for today, ada soalan tak nak tanya? Okay, bahagian correlation factor ni saya nak discuss next class Okay, ada soalan tak untuk example ni untuk ABC? ABC is same thing, only that the value of the temperature and pressure je lah berbeza. Ada soalan tak nak tanya?
Tak ada, Doktor.
Faham Saya tak laju sangat Okay, so okay je kan. So apa ni, kalau nak lebih faham, mungkin siapa-siapa yang tertidur tadi untuk saya waktu online class ni kan, biasalah puasa-puasa kan, tengah hari Jumaat. Okay, we have so many other factors that might disturb our focus. Okay, you find it difficult to understand, alright, and perhaps you can go to the future and you see ambil part-part yang kamu tak faham tu je. Okay, tak perlu nak tengok semua pun. Alright, so okay, next week I will continue just a bit on this part, and then we will discuss about this correction factor here, and then right after that we're going to straight away go to the molecular diffusion in liquid. Okay, please make sure that you have the what we call it, the notes with you. Alright, itu hari Rabu, so hari Jumaat saya kemungkinan cuti sebab hari Khamis minggu depan cuti nuzul Quran kan, so cuti hari Jumaat tu, so perhaps hari Jumaat tak ada kelas lah, saya akan post video je untuk kamu tengok. Okay, for molecular diffusion in solid perhaps, right. And then lepas tu kita jumpa minggu ketiga, seminggu sebelum raya tu. Alright, secara online baliklah live lecture pada hari Rabu. Okay, so if that's, thank you so much. Okay, for those of you give an attention and respond to me, thank you so much. Alright, still early to say selamat berbuka, but yeah, there is selamat berbuka lah, okay, pada pukul 7.30 nanti. Okay, thank you. Assalamualaikum.
Thank you, Doktor.
Thank you, Doctor.
Thank you,